Every time you flip a light switch or send a text or just, use your computer, you're tapping into some of the most bizarre and powerful rules in the entire universe. I'm talking about the rules of quantum mechanics. So in this explainer, we're going to bridge that gap. We're going to connect those strange, mind-bending quantum ideas directly to the tech you use every single day.
So let's kick things off with a bit of a riddle. What could a modern LED light bulb, a computer microchip, and a magnet that's just floating in midair possibly have in common? I know, it sounds a little random, but the answer for all three is exactly the same. They are all, at their core, powered by the principles of quantum physics. Let's dig in and see how.
All right, first things first, we have to ask, why did we even need a new set of rules in the first place? For hundreds of years, classical physics, the laws of Isaac Newton, did an incredible job explaining our world. The world of planets, of billiard balls, it all made perfect sense. But when scientists started peering into the super tiny world of atoms and electrons, those old rules they fell apart completely. And what's so wild about this is just how big of a shift it was. I mean, think about it. Classical mechanics gave us this comforting certainty. You could know exactly where something was and exactly where it was headed. But quantum mechanics, it throws all that out the window. It says you can never know both the precise position and the momentum of a particle at the very same time. Suddenly, everything became a game of odds, of probabilities, all run by a totally new revolutionary equation. And that new rulebook is the Schrödinger equation. Now, don't worry, we are not going to get bogged down in the math here. But here's the big idea you need to grab onto. This equation is the absolute foundation of quantum mechanics. You can think of it like a new operating system for the subatomic world. It doesn't tell you where an electron is. Instead, it describes this wave of probability. It tells you where an electron is likely to be. And that one idea, that is the bedrock for everything that's coming next. So, how do we get from these abstract waves of probability all the way to a smartphone? Well, the very first step is to see what happens when these quantum rules are applied to a whole bunch of electrons, all packed together inside a solid material. This gives us this really powerful idea called energy bands, which you can kind of picture as an energy superhighway for electrons. In materials that we call conductors, think of something like a copper wire. These energy bands actually overlap. So what does that mean? It means there's no energy gap for an electron to jump across. They can just hop into what's called the conduction band and start moving around with almost zero effort. It's like a wide-open 8-lane superhighway with no speed limit. That's why metals are so good at conducting electricity. Now, on the complete other end of the spectrum, you've got insulators, like rubber or glass. In these materials, the gap between where the electrons normally hang out, that's the valence band, and that conduction band superhighway is just enormous. It's like the highway is on the other side of the Grand Canyon. It would take a massive jolt of energy to get an electron over there, so for all intents and purposes, they're just stuck. No current can flow. And this brings us to the hero of our story, the semiconductor. This is our Goldilocks material. It's just right. The energy gap is there, sure, but it's small, it's manageable. It's not a canyon, it's more like a little curb. With just a little nudge from some heat or a bit of voltage, we can actually coax electrons to hop that gap and start conducting. And this ability to be controlled, to be turned on and off, that's what makes them so incredibly powerful. This table just lays it all out so clearly. Just look at those energy gaps. They're overlapping for conductors, tiny for semiconductors, and absolutely massive for insulators. So here's the key takeaway, the crucial point. With a semiconductor, we can control its conductivity. We can turn it on and off just by managing that small gap. And that simple idea, that's the fundamental switch that all of our modern electronics are built on. Okay, so having a material that you can control is one thing, but to actually build something useful with it, scientists had to figure out how to precisely engineer it, how to hack these semiconductors. This is the part where we go from just a boring slab of silicon to a really sophisticated electronic component. And the key technique here is something called doping. This is where you intentionally sprinkle a tiny, incredibly controlled amount of a different element into that pure semiconductor crystal. It's kind of like adding just a pinch of salt to a recipe to completely change the entire flavor. And the precision here is just mind-boggling. We're talking about surgically adding just one specific impurity atom for every million or so silicon atoms. It's this amazing atomic level control that really unlocks everything.
Now, doping basically comes in two flavors. With N-type doping, we add impurities that have extra electrons to give away, which creates a material with a surplus of negative charge carriers. Then there's P-type doping, where we add impurities that are actually missing an electron. This creates these positively charged holes. You can think of them like empty parking spaces that are just waiting for an electron to come and fill them. And now for the real magic trick. When you take a piece of P-type material and stick it right next to a piece of N-type material, something incredible happens. Right at that boundary, the extra electrons from the N side rush over to fill the holes on the P side. This creates this thin, neutral zone called a depletion region, and it acts like a barrier. And what you're left with is a P-N junction, which is probably the most important component in all of electronics, a perfect one-way street for electricity. So we've built this elegant little one-way gate for electrons. What can we actually do with it? Well, it turns out you can build pretty much the entire modern world. Let's just run through a couple of quick examples. First up, you've got rectifiers. The electricity coming out of your wall outlet is alternating current, AC, which means it flows back and forth. But almost all of your electronics, they need stable direct current, DC. Well, that one-way PN junction is the perfect tool to just chop off one direction of that flow, converting AC into the DC that powers all your gadgets. Every single power adapter you own is doing this right now. Next up, LEDs. What happens if we force current through that PN junction? Well, electrons and holes get pushed together and they recombine. Now, according to quantum mechanics, when an electron falls into one of those holes, it has to release some energy. And in an LED, that energy is released as a photon, a particle of light. And the color of that light? That's determined by the size of the material's energy gap. It's a direct link right back to our quantum principles. And a solar cell? Well, a solar cell is basically just an LED running in reverse. Instead of putting electricity in to get light out, we put light in. When a photon from the sun hits the PN junction, its energy is just enough to knock an electron out of its spot, creating a brand new electron-hole pair. The junction's built-in barrier neatly separates them, and that creates a voltage. And just like that, sunlight becomes electricity. Okay, so from semiconductors, we've basically built the present. But there's an even weirder quantum phenomenon that points toward the future, superconductivity. It's a property of matter that could totally revolutionize technology as we know it. So what is it? Superconductivity is the state where a material's electrical resistance drops, and not just low, it drops to exactly zero. This happens when you cool the material below a very specific critical temperature. It means electricity can flow through a superconducting loop forever without losing a single bit of energy as heat. And this chart just shows how unbelievably sudden that change is. Above that critical temperature, the material has resistance, like you'd expect, but you cool it down just 1 degree below that point and bam, the resistance completely vanishes. It's a true phase transition, just like liquid water freezing solid into ice. And somehow, it gets even weirder. Superconductors don't just have zero resistance, they also actively push magnetic fields out from inside them. This is called the Meissner effect, and it's the reason you see those incredible videos of magnets just floating, levitating effortlessly above a superconductor. The magnet is literally riding on a cushion of its own repelled magnetic field. And that really brings us to our final thought. The biggest challenge right now is that all this only works at incredibly cold cryogenic temperatures. But just imagine, what if we could crack the code? What if we could create a material that superconducts at room temperature? Imagine a power grid with virtually zero energy loss, saving us billions. Think about ultra-powerful magnets making fusion power a reality, or continent-spanning maglev trains, or a whole new generation of quantum computers. It's a glimpse into a future that's built on the strangest and most powerful rules in our universe.